In 1999, I started as a freshman at Dansteel, and now, 20 years later, I'm coming back to visit my successors. A lot is still as I remember it, but there has also been a lot of changes. In this podcast episode, we will take a deep dive into the production of very thick plates, together with my new friend Eugene. Hi, Eugene. Welcome to the podcast Everyday Metallurgy.
Hi, Peter. Thank you very much for the opportunity to speak about
I,
metallurgy.
yeah, Eugene, I am back to where I started because my first job ever after finishing my education was at Dansteel. I worked at the Danish steel mill, and now we are back. And I would love to see what has happened. It's more than 25 years ago. So has anything at all happened, or is it just the same as when I left? Uh,
Yes, actually, it was an interesting surprise when we were starting texting each other that you told that you were at Dansk Valswerken
yeah,
working before. And by the way, I remember when you came to see the mill, you still have some colleagues who was working at that time, and you
yeah,
had a talk. It was also interesting
yeah. It was
to
great
see.
to
Yeah.
see the old friends again.
Because I'm working at Dansteel for 13 years now, and sometimes I feel that it's really a long time. But we have a
Yeah,
colleagues who are working for 25, 30 years,
yeah.
first in old company and
You're
now a
still
new
just a
one.
newcomer.
Yeah,
Yeah,
yeah, green guy.
yeah. But Eugene, will you give a short introduction to yourself initially?
Yes, my name is Eugene Goli-Oglu. I'm at Dansteel 13 years. I'm a head of technology, product development, and technical sales support functions here at Dansteel. I have a PhD in material science, which actually was related to production of steel heavy plates for welded structures. And before, I also have a master degree in material forming as well, and like a small addition, like international economy as well.
Okay,
Yeah.
so you are just spot on the right person because we're going to talk about uh, thick walled steel plates today. Can you give a pitch on why are thick walled plates interesting today?
Yes, and not only interesting, but actually quite important for different key industrial segments. But
Mm,
let's first, I will show, I made some small presentation, and let me first introduce Dansteel and what we are producing in general, and then we will go into details. Is it okay for
mm,
you? Good. Yeah. So Dansteel is not far away from Copenhagen, and like a spot, the main equipment we have, it's a furnace which we are using for to preheat slabs, semi-finished products,
mm,
also steel one. And then we have mill quarter, big stand with 12, with 14, maybe 15 meters tall. And then we also have accelerated cooling for more
mm,
advanced material to be used. And then other equipment, we have around 20, 23 operations from material was a slab till material becoming a final plate, like a final
mm,
product. And we are producing plates in thickness from 5 millimeters, quite thin one,
mm.
to 256 millimeters. This is actually the maximum gap
Yeah.
which plate could pass inside the walking rolls of our stand. And
Okay.
yeah,
Yeah.
yeah, and then maximum width of the plate is 4 meters,
Hmm.
and then maximum length of the plate is up to 30 meters in length, and then the total weight could be up to 63 tons of each individual plate.
Yeah.
Of course, it will not be maximum dimensions in each size, but in general, this is our
Yeah.
maximum capable
Mm.
capabilities or performance. Dansteel.
Quite big.
Yeah, and about heavy plates, steel heavy plates, they're used in several different industries. Like in main markets, we do have, first of all, wind, both onshore and offshore. We have shipbuilding. We have pressure and boiler and pressure vessels, and bridge building. There is also other industries which also require steel heavy plates, but they are normally slightly smaller. In the end, we have around 8 niche, I would say.
Okay.
Because when you are passing the wind mill, and it will be either onshore or, for example, if you are traveling by ferry to Germany, then you could see the Kriegerschlag offshore field, and the tower and the foundation and transition piece will be produced from steel heavy plate.
Okay.
The same as tower when you are passing just a normal highway, it will be also produced from steel heavy plate. Bridges, it's a little bit more options. You could make it from concrete, but it's a lot of bridges made from steel, and in this case, heavy plates are used quite often. And for now, our maximum thickness, which we have delivered to Belgium bridge builder in 2025, was 147 millimeter in TM plus ACC, which is the most advanced technology. And then we're also delivering thicker plates for basements, for complicated connections of the bridges, and etc.
Wow.
For shipbuilding, normally it's a thinner plate. We are starting our portfolio from 5 millimeters, and then normally it's up to 35 millimeters, depending on the vessel, depending on connections, depending on the total weight of the vessel, I would say, in this way. And then pressure vessel and boiler segment, it's also a lot of differences depending on the type of pressure vessel, depending on the what will this pressure vessel carry inside. Either will be dangerous liquids, either it will be gas, either it will be something different. And we will touch a little bit in presentation about this as well.
Yeah.
My proposition is to go application by application, if you would like to.
Yeah, that'll be wonderful. I'm curious to see how it's connected and how it's made. Especially the thickness of the wind turbine towers. It sounds crazy, but they are extremely thick.
And they're becoming thicker and thicker, actually, because if we will see the tendency 10 years ago and now, there's a big difference in terms of wall thickness, because towers becoming more powerful and nacelles becoming bigger and more powerful as well. If 10 years ago, the normal maximum generation was around 5-6 megawatts. Now it's going up till 15. And there is also prototypes which are going up to 20 megawatts each tower. So construction is huge, and it's require huge support. And this is huge support could be done mainly only by heavy plates, which are used. So here I was trying to make some kind of quick description of the foundation part and the transition part from the tower, and you could see it from the middle figure. So this is a typical monopile foundation structure, where it's gray one, it's offshore tower part, and then it's transition piece, and then it's a monopile foundation, which will be partly under the water and partly in the ground. And this is how it looks in reality, also quite challenging and quite big, with with a maximum diameter could be above 10 meters easily. And then here I have added in the same way the thickness of the plate which will be used. It could be different project by project, depending on the soil condition, depending on the weather condition, on the wind power, and so on. This part is not for us, it is for fabricators. We just get in specification and trying to say yes on such with with sometimes extra demands and requests. And there you see that in case of the tower, on the top of the tower, it could be easily a 25 millimeter plate.
Yeah.
And then when we are going closer to the water, then it starts to grow till up to 75 millimeters. It's also possible for the bottom section. And then we have transition piece. It could be a different format of this transition piece, but this sounds like a classical one. And then thickness of the plate will be increased. And then we saw some specification which are coming to 115, 120, especially in this section where it's already connected or close to the sea, for example.
Yeah.
And then it's a bottom side, which is a black, and there it's also depending on condition of the soil and the depth of the water in the place of installation. It could be also vary from around 75 till 100, 150. And you see here is a gray part. This is what we estimated will be like increase in next 5-7 years.
Wow.
So we think that it will be more and more.
Yeah.
There is also, this one is, you have a question?
Yeah, so when you see a wind turbine, you actually only see the tower, but that's a minority of the steel used. The majority is hidden away.
Yes, for offshore tower, the main tonnage of the steel is actually under the water. For onshore tower, foundation normally done from concrete, and then the tower is from steel. There is some percent of towers which could be done from concrete as well, and they're sometimes popular. And I actually also thought that there is some options if it's smaller one to make it actually from wood. But still steel and steel plates are becoming still continue to be the most popular material for these constructions because of combination of factors. So it's a price, quality, and resistance to long-term use of the tower. Because according to documentation, it's have to be at least 30 years, and then with a possibility for prolongation for 5 or 10 years, something like this. Of course, actually steel, which is, for example, steel bridges, they still will be in good condition even after 50, 60, 70 years.
Yeah. The foundation, is it installed in black condition or is it painted to protect it?
Bottom side, it's in black condition. And then transition piece is this one typically has yellow color. I think it's a requirement of the standard to have it in this way. So it's visible for the ships because in the bad weather, this is important part. And then the tower, it will be also painted, of course.
Yeah.
And by the way, we were talking about monopiles, like main part of the the main type of foundation. There is also a floating type of foundation, which describes here, which is also quite thick in terms of thickness of the plate. And then you see its design is made so wind tower is actually floating like a ship or like a platform on the sea, and do not connect directly to the ground except of some mooring piles, for example.
Yeah.
But this is something which is still in development. And the advantage of these platforms is that it's possible to install in deep water compared to monopiles.
Yeah,
Because
of
as I
course.
remember, maximum depth of the water for monopile is around 50, maybe 60 meters deeper. And after this, then it's coming floating, which is still in development, as I know.
Yeah. And they are big.
Yeah, super big, especially when you're close to them.
Yeah.
You see here the total height of the tower of the construction could be up to 230 to 150 meters. So yeah, incredibly big and becoming bigger and bigger.
Yeah. And the alloy, is it special alloys for this when it's offshore to resist the corrosion from the salt water, or are there other demands for the alloys?
As far as I know, the corrosion will be done, protection will be done in different way. So it will be done in terms of electrolysis, and this will be the way how it will be protected. And from side of chemical composition, yes, there is a difference between onshore towers and offshore towers, and there is a difference between offshore towers and offshore foundation, because the simplest construction in this segment is onshore towers, which is normally produced from standard S355 as rolled material, which is, I would say, basic material. And then for offshore towers, it's normally required that they have to be produced from normalized or normalized rolled material, which is improved technology, and commonly with some extra limitation in chemical composition to meet the maximum CQ requirement of 0.43 to be able to weld this material in easier way, I would say. And then foundation and transition piece, they're normally made from more advanced material using technology TM and TM plus ICC, which require some extra technological steps in production, and normally aiming to have quite low carbon equivalent level to be able to weld thicker material with better efficiency and with a guarantee of good and reliable properties in the weld heat affected zone, including fusion line and other well-known welding zones of weld joint.
Yeah. I heard a story some years ago that in a tower, the stair is attached inside the tower with magnets to avoid welding, because weldings of the tower will make it weaker, and therefore if you weld it you would need a lot more steel. Can you confirm that welding makes the strength lower?
I have small experience in engineering, something like 17 years, but I know that engineering is something which is connected to development and creativity. I would say so. I didn't hear I didn't hear about this before, but I could imagine such could be possible.
Yeah.
I will be a little bit more conservative and still prefer to use welding for the stairs, especially because it's also connected to the safety, and we know in many industries there is right way to saying that safety first. Yeah, so I will prefer welds than magnets.
You don't want to walk on magnet stairs.
I like the picture, but yeah, I will prefer to use stairs which has connection with welds, bolts, but welds are better.
Yeah.
Because it's also, if to compare steel which were produced 20 years ago and steel which are produced now, it's a lot of weldability investigation were made to make welds more reliable and to make it possible to have stable, good level of properties, including hardness, strength, and low temperature toughness for this material, so it will not be broken after 10-15 years. Also fatigue or after loads, because we also know that one of the loading which tower and the foundation could have, it's a fatigue loads due to the wind cycling. Yeah.
Let's jump to the next.
Next segment, what I would think will be interesting for this podcast is the use of heavy plates for pressure vessels. And the interesting part with pressure vessels that if to compare pressure vessel with a tower, it will be very different. Between tower, in our eyes, it's more or less a standard structure. Of course, there is a lot of variability in thickness, but in the end, it's a one type. But there is several types of pressure vessels depending on the final use and what they will carry inside. Right now, we see the good movement in CO2 storage tanks, for example, because European Union is trying to be CO2 neutral and have zero emission in the end, and it's a combination of discussion, but also something already be done, and some projects are already implemented, and Dansteel is participating in this project. As soon as this is a new direction for pressure vessel, then there is possible to use different concepts of steel heavy plates, which will be used for pressure vessel depending on design, and in this case, fabricator will choose what they would like to do, because we see now the trend that those kinds of pressure vessels for CO2, the customer fabricator prefer to make it like storage tanks, and here is one of example which was produced from Dansteel plates. And in this case, customer could choose either standard strength level, which is P355, and L1 and L2, for example, which means that it's will be suitable for use at -40 and -50 degrees even. Either P460, also an L1 and L2, which is also -40, -50. The difference between those concepts that in case of S355, if you're using the same pressure, wall thickness should be higher. And in case of P460, due to the higher strength on material, wall thickness could go down, and this difference is around 25-30%. So from one side, you are investing more into material, but from other side, you are saving on the wall thickness, and you are saving on the weight of final construction. And then we also see the tendency that if it's installed on the land, for CO2 capture or temporary storage or long-term storage, then it will be P355, thicker wall. But for example, if it will be for transportation, then it's more interesting to have higher strength grade and the thinner wall, and then your construction will be lighter as well. And here is two examples. We also wrote few articles about this one. It's a small picture, but you still could probably see it when it's a cluster of these storage tanks of 6 or 8 together standing. And then you are they are installed in the this project was installed in Netherlands, close to the plant, which is producing ammonia. So in this case, CO2 is bystand product, which will be captured here. And this is a way how company is reducing their CO2 footprint.
And do they put it underground after storing it?
It could be several solutions, and yes, and I will show you now next slide, which is quite interesting as well. This is slightly another project, and this is different concept. And here, customer was using different type of steel, and this is a layout of the final pressure vessel, how it looks like. And in the end, they are installed in their ship, special one, and will transport CO2 from Esbjerg port in Denmark to gas platforms in the North Sea called Nini for permanent storage of CO2 in this former location of natural gas.
So they are sailing back and forth with it.
Yes. I know that there is also another concept to make a pipeline, but this is for less deeper water and require another level of investments. And here, this kind of transportation is also give flexibility.
Again, the weldings you showed on the previous slide, I could see there were multiple weldings. How do you secure that the weld seam also fulfills the low temperature demands?
When for the new products, we are performing weldability testing to be sure that after welding our steel heavy plates will still be in a good shape, I would say, and will guarantee the level of mechanical properties which will follow the requirements of the standards. And it's two options: either to make it here at Dansteel or close to, either we could also send the plates or coupons to our customers, and then they will weld it using their equipment and then test it and give green light, or if it will be some issue, we'll have some discussion how to improve it. Normally, this kind of material will be welded with submerged arc welding with heating input around 2 kilojoules. And then it will be split into sections. And then here you see this is a base material, and this is a weld, and this is a heat affected zone. And then it will be tested in many different places. The most normal practice is to test the weld here on the face side from both sides, in the middle, and also on the root side of the weld. And then normally we are testing in the middle of the weld, and then at the fusion line, and then fusion line plus 2 millimeters, and fusion line plus 5 millimeters, and fusion line plus 20 millimeters, to be sure that each small section of the weld will still resist to impact loads at minus temperature. And will guarantee a low temperature toughness both of base metal and of welding joint in total, like a one construction, like a one unit. And then we are also making sometimes more advanced investigation. Here below you see this is a part of the weld and the part of the base structure, and then it's colors which were which we are getting from the micro harness measurement, which is making a lot of dots like needles, like this, and like in matrix, and then showing us more dynamic picture and with high resolution, I would say, where we could have potential problem or not. If the hardness level is reaching above 300 Vickers, then it's a question for discussion and how to use this material. But if it's 250, 260, depending on the material, then it's a reliable weld. And of course, as this is for P460, for higher strength grades, for P355, it will be normally 100, 210, 220 Vickers.
Yeah. So the test being made, all these spots you showed, notch test at minus 50 degrees C.
Depending on the application, but yes, it will be made either at minus 20, either at minus 40, either at minus 50 degrees.
Yeah. We should have known that before building the Titanic.
And actually, at certain point, as I remember the history, impact test became into life or was created after Titanic crash, but I'm not 100% sure. But as I remember, there was no such testing at that period, and then they start to come because as big a structure, ship, tower, bridge, as more loads in different directions at different temperature ranges could come. And then when choosing the right material, you have to take this into account. Hopefully we have a lot of regulations which helping us and helping fabricator to meet with their demand and the requirements and our capabilities and possibilities.
Yeah. What is it in the steel that enables it to still be tough at minus 50?
It's a combination, I would say, a combination between chemical composition and technology. But in general, as lower carbon, as better toughness. As lower sulfur and phosphor as better toughness because then purity of the steel is much better. But then it's also another extra points like microalloying of the steel, microalloying by niobium, by vanadium, by titanium in combination or in single way. Also give you extra values of low temperature toughness. And if, for example, 50 years ago, the normal level of low temperature toughness at, for example, minus 20 was around 60, 70 joules, now we're getting material with impact toughness 200 joules.
Wow.
Yeah. Same as at minus 50. There is a different type of technological where as-rolled material is the most easiest material, and then TM plus ACC is the most complicated. But in TM plus ACC technology, you could get impact toughness 300, 400 joules per square centimeter.
Yeah. So many impact hammers, they are out of spec when you go above 300.
Yes, and that's why we have installed powerful one with 450 joules.
Yeah, okay. Yeah. Yeah. And the microalloying with niobium, vanadium, is that to remove the carbon to make very small inclusions of carbides? Or is it to make fine-grained homogeneous material?
Depending on the technology. For example, in case of as-rolled technology, addition of vanadium will work like strengthening element, creating nitrides and carbides of vanadium, depending on content and depending on equilibrium. And will reinforce the steel, I would say, with the dots, which are carbides and nitrides of vanadium. But in case of normalizing or TM plus ACC, niobium and less, but still vanadium will make better grain refinement. because during the technological process of heavy plate production, when you're preheating the steel, your grains are becoming really big, with a size of 100 nanometers, for example. And then during the process, you're making reduction of the thickness, but at the same time, you start to deform the plate, deform. And with this deformation, in certain regions, grains, they are starting to pass recrystallization phase. So they are creating again and appearing again from small one, and then start to grow again. And then when they are reaching certain temperatures and energy level is on different stage, then you start deform and make some pancaking of these grains and make smaller defects, dislocations and other one in these grains. And then later on, when it will be the final transformation of material from austenite to ferrite or bainite, or secular ferrite, which is the best in this case, then from those small dislocation and small defects and grain boundaries, they will become like a place where new grains will born. And depending on the size of this one, you are getting the final size of your grains inside their steel. Here is, for example, one picture where you see how steel looks like in final condition if to use optical microscope. In this case, where it's a lot of smaller grains, which given much more resistance to the steel to resist from cracking, for example, because crack need to pass much longer route if you have a lot of smaller grains compared to one big one.
And are there an isotropy in thick plates, or is that only seen in thin plates that are cold rolled?
Yes, there is also anisotropy of properties, and as thicker plates as more complicated to make deformation, because the peak of deformation, it will be in 1/8 of plate thickness, and then it will be lower and lower. And I have it. And then you have to combine both technology and both chemical composition, aiming to achieve as better uniformity of the microstructure as possible in condition which depends on thickness and grade of material. Here, for example, there is example where you see for person who is looking in optical microscope, it's obvious, but then, for example, condition 1 is given certain ununiformity, condition 2 is given certain uniformity, but if you reach the optimal condition and optimal connection between chemistry and technology and the process regimes, then you could get quite nice uniform fine-grained microstructure, and this is what we are aiming for.
I like this. That when you see a steel mill, it just looks the same. It's just a slab coming in, it's being rolled, and it goes back and forth, and that's it.
I think that this is a phrase that devil in details. This is exactly about these small things.
I love that you can, if you do it wrong, make it wrong.
Yes. But then I believe that you still sometimes is making not the best, and then this is a possibility to learn and to improve the process. And another application which I want to show, it's bridge building as well. Because as I told that bridges could be both produced from concrete, produced from steel, depending on the project, depending how fabricators see it. I pity, but I do not know the balance between concrete and steel bridges. But steel bridges have some advantages because they are lighter and they could work longer. And here, like an example, and actually, what you could also do, there is two ways. You could, for example, supply plates to build a new bridge, but you can also supply plates for bridge modernization, for example. And this is actually quite good example I would like to show. This is a bridge in Sevilla. Sevilla.
Where is it?
Sevilla, Spain.
Yeah.
And then it was a concrete bridge. And then because of the traffic, because it's from 70s or 60s, as I remember, because of the traffic, the community have decided that they want to have 3 lanes instead of 2 lanes in each direction and extend traffic. And then what they are doing on the existing structure, they will add steel plates around to reinforce it, and also will add steel plates on the bottom side of the bridge. And then it will give possibility to solve the problem with the traffic in the city center of the industrial part of Sevilla. A specific part of this one, that in this case, it's not a fully black steel is used, but it's some niche products, which is called weathering steel.
Is that cartan steel?
Yes. This is a modification of cartan steel, which in European norms called weathering steel, and the steel has better performance if to look on it from side of corrosion resistance, atmospheric corrosion resistance. And then it means that steel is actually slightly more expensive because for these purposes we are adding chromium and copper to the plates, to the steel when melting. And but there is advantage that you don't need to paint it actually for many years. And we see now that it's not only bridges now, bridge builders who are interested in this material, but sometimes it's also buildings which are partly made from weathering steel, and it's sculptures because it has a nice rusty look. I've
seen several buildings of that. I had the impression that when you add copper, you have the risk of hot tears or hot cracks. And how do you avoid that when you're welding it?
In this case, we are probably talking about higher copper addition, because in this for this material to make it good enough for atmospheric corrosion, we are adding 0.35% of copper, which is not so big for potential issues with the cracks, and still good enough for making corrosion index above 6.0, which is when steel is considered like resistant to atmospheric corrosion. And at the same time, by the way, in the recent 5 years, we have also made a lot of developments here, and we were able to decrease carbon equivalent from 0.47 to 0.44, which also actually improving the welding of material. And we see that in 2 years, we see some kind of boom for this kind of material, and we are also almost ready with our own brand in weathering grade called Quernox. I think we are finalizing the special website for this, so it will be available soon.
Yeah. What is the chromium content?
0.40, 0.50.
Okay.
Also
So
not so high. And
no.
then in addition to protect steel and to make it stronger from one side, and then to avoid surface defects from other side, we are also adding combination of niobium, vanadium, and titanium like microalloy
Hmm.
to this material.
It's everything from the periodic.
A little bit
Yeah.
from the top side.
Yeah. And here thickness were up to 120 millimeters, I remember it.
The maximum for this project, it was 130 millimeter plates, which were used in foundation parts, of course, to make it solid.
Yeah.
And then in the top of the bridge, it's 10, 12 millimeter, 10, 8 millimeter even. So like a standard in the bottom of the construction, you have thicker plates, and then you are decreasing the weight to make it stable.
Yeah. When now we talk the production of steel, how is that produced? Is this made with scrap or is it made with a blast furnace and raw material ore?
Metallurgical society at present point is somewhere on the turn, because traditionally for last 30 years the main process is BOF, basic oxygen furnace.
Yeah.
And this is a cheap, reliable process, which at the same time bringing some extra pollution. Now with new targets in terms of CO2 and so on, electric arc furnaces are becoming more and more relevant, and a lot of industry and a lot of different companies are looking into this solution. Some of them already has, some of them want to invest in this one. And this electric arc furnace is working on the scrap. Could work fully on the scrap, could work partly on the scrap depending on the technology, but is able to reduce emission of the steel. I made one slide, very brief one, comparing three possible solutions here, where it's a classical BOF, and the reason why it's bring higher pollution or standard pollution, I would say, because it was a standard for many years. This is because of amount operation plus use of fossil material like coal and coke and also natural gas in this case. And then the typical pollution is around 1.8, 2.4 tons CO2 per ton of the steel. Depending on the electricity, depending on the gas, depending on the operation and the efficiency of the process. And now it's more and more people looking at possibility for electric arc furnace, and then it's actually only two operations: scrap plus furnace, and nothing in between. And for furnace, you need electricity. And if you could get electricity from green, from wind, for example, then even less pollution you will have. Then it's also a possibility to have scrap plus DRI, which is directly reduced iron, and then to have some kind of balance in using scrap and in using this DRI, which are also coming from pellets. And each process has advantages and disadvantages. We are now trying to work a little bit with electric arc furnace slabs. The problem of these slabs actually is that they are quite expensive. And the quite expensive, I would say that they are 30% expensive.
Wow, higher price than the buff.
Yes. And then it's also a lot depends on the scrap price, because as far as I see the calculation, if everybody will decide to make material from the scrap using electric arc furnace, there will be not enough scrap. Because scrap is good, it's recycled of the steel, but it's still limited condition. You still need to dig something from the ground, and then potentially a DRI solution could help with this. So for my opinion, for the next 10 years, the balance will be changed between BOF and EAF and those two options, but all of them will be still relevant because in the end it will be some balance, but globally CO2 emission will be decreased. Yeah, and then it's several places, several countries, for example, which are able to generate green electricity. They could deliver semi-finished product slabs with final CO2 something like 0.3, 0.5 ton CO2 per ton of steel, which means that it's 3, 4, even 5 times less compared to BOF. And we need to remember that before BOF, we had another type of production, which was Marsen, it's called, and this was even high in pollution. So it's going.
And your customers are in the green segments. So it's the carbon capture, it's wind turbines, it's the green segment, you could say.
Yes, and pressure vessels also green segment. But if you're asking, would they like to get EAF steel? As I see, yes, they would like to, but the price question is still relevant. But I think that when new technology will come and as more attention to this direction is given, the more optimization could be done, and this means that price level could go down to more or less a good commercial business cases, I would say. We are trying now several suppliers of green slabs, both from Europe, and we are also looking for out of Europe as well. We have a sister company who is producing green slabs as well in Italy. And we are taking small portions of those slabs to test it for wind foundation and for wind towers. But for now, it's on development stage still.
So we're at the end.
Good. It was quick hour.
Let's sum up. Eugene, what is the next step for Dansteel? Where will Dansteel be in 5 years from now?
Good question. I hope that we will continue to get good projects from wind segment. I hope that we will have more projects and possibilities to participate in offshore foundation part. We see that pressure vessel and boiler segment is developing as well, and we are participating in this development as well, and would like to continue. And we are trying every year, or I would say every cycle, to optimize our existing process to make it more stable and, if possible, slightly cheaper, to have a good competition, because competition from inside the Europe is great, but also competition outside of Europe is becoming bigger and bigger. It's not only in industry segment we have in Europe competitors from the East, it's in all types of industries. And this is a good reason to think how we could improve our business process and improve our product to compete in European market, but also outside, because we are shipping to India, we are shipping to Turkey, we were shipping to US before this tariff wars. Now it's commercially protected, I would say, from European material. But we are trying to find a niche and try to be flexible in the market. And of course, our main aim to make our customer happy and feel that they are in safe position when they are working with us.
Yeah. Eugene, the last thing I would like today is I know that you have written several papers and articles in magazines, and they are high level. And I know that some of the followers they like to go deeper. Can you share a link to these articles in the post notes of this episode?
Yes, but we should discuss it additionally how to do it because some articles are protected by the journal rights, authority rights. And by the way, we just published in edition 2 of 2026 in German journal Stahl und Eisen the latest article about big offshore projects which Dansteel were participating in 23-25. And it's article number 100 in my scope.
Oh, yeah. And what about the Dansteel homepage? Are there anything to look deeper into there?
Yeah, it's possible to find it there at some way.
So I will also add a link to that.
Yes, please.
Yeah. Thank you very much. I really enjoyed it. I learned a lot more than I expected. And my conclusion is that something has happened over the last 25 years since I left. So congratulations with the big expansion and these new segments that didn't exist 25 years ago.
Yes, we are trying to follow the market and sometimes trying to create it and create some niches for the new product if we see such capabilities.
Wonderful. Thank you very much. See you soon
Thank
again.
you.
Maybe I'll come visit you again.
You're very welcome to come again.
Thank
Bye.
you.